Let's dive right into this explanator. Today, we're taking a journey into the fascinating and, sometimes a bit messy, but incredibly structured world of scientific inquiry. If you've ever wondered how scientists actually go about discovering the invisible rules that govern our universe, well, you're in exactly the right place. We're going to break down the exact steps that turn a simple, everyday question into a rock-solid scientific conclusion. To do that, we're pulling the practical foundations right out of the Cambridge IGCSE Physics material and transforming them into your ultimate toolkit. We'll be looking at the exact framework taught to physics students to help them think like true investigators. And hey, this isn't just about passing an exam. It's really about mastering a way of thinking that lets you confidently tackle real-life problems. So here's our game plan for today. First, the inquiry process. Second, planning your experiment. Third, observations and data analysis. Fourth, evaluating methods and errors. And finally, ideas, evidence, and controversy. Okay, let's kick things off with Section 1, the inquiry process, covering the core steps of literally any scientific investigation. Every single successful experiment, whether you're just measuring a cup of liquid's temperature or trying to verify some massive, complex physical law, follows these four essential logical steps. You plan, you observe, you interpret, and you evaluate. It's like a giant puzzle. If you skip a piece, the whole investigation just falls apart. It's this beautiful, continuous loop of logical deduction. Moving to Section 2, planning your experiment. This is all about setting the stage for accurate discovery. Look, before you even touch a piece of equipment, you absolutely need a bulletproof plan. It starts with a clear hypothesis. Basically, your highly informed guess about what's going to happen, and a rigorous risk assessment to make sure you're actually doing it safely. Once that's set, you have three primary control mechanisms. You've got the independent variable, which is the one thing you purposefully change. Then there's the dependent variable, which is the factor you measure to see the effect. And finally, the most crucial part, you have to strictly control absolutely everything else so that no random external factors mess up your hard work. A massive part of that planning phase is choosing your tools. The key to precision is actually knowing the limits of your equipment. Think about a standard meter ruler. Its smallest division is usually 1 millimeter, right? Well, generally, you can read a measurement down to about half a scale division, so that gives you a precision of 0.5 millimeters. Knowing that built-in limit is absolutely vital for understanding just how accurate your final data can actually be. All right, Section 3, observations and data analysis. Let's talk about capturing and organizing your findings safely. So you should always set up your results table before you take a single measurement. It's a lifesaver. You put the name of the measurement and its specific unit right at the top, like mass of load / kilograms for kilograms. Doing this keeps your data incredibly clean, and it totally saves you from having to write out the units next to every single number down the column. Now, when you're in the thick of it, pulling in that data, there are a few golden rules. You want to aim for at least 8 data points, spreading them over as large a range as you possibly can. You also need to repeat your measurements and calculate averages. That's how you ensure real accuracy. And please, remember this massive pro tip. Do not dismantle your equipment until you have completely finished your analysis. If you suddenly realize you need to rerun a weird measurement, you'll be so glad your setup is exactly as you left it. Once you've gathered all that data, you'll usually plot it on a graph. And as you look at those 8 or so data points mapped out, you have to ask yourself a critical question. Does this data tell a cohesive story? Is there a clear, undeniable trend line? Or is there some weird outlier in there just throwing the whole thing off? An anomaly. If you do spot an anomaly, you can't just sweep it under the rug. You have to explain exactly how you dealt with it. Maybe you went back and retested that specific point. But once those outliers are handled, you draw your line of best fit and you calculate the gradient. That establishes the actual mathematical relationship between your variables. It's kind of magical. It's the exact moment where your raw, messy data transforms into a completely justified conclusion. Which brings us to Section 4, evaluating methods and errors. Because, let's face it, we have to diagnose the imperfections in our experiments. Listen, no experiment is perfect. It's so important to understand how our own setups can actually trick us. First up are systematic errors. Now, these aren't just silly mistakes you make. These are flaws inherently built into your apparatus or your design. For example, if your measuring scale is calibrated incorrectly from the factory, it's going to consistently throw off all your measurements by the exact same amount in the exact same direction every single time. On the flip side, we have random errors. These are the naturally occurring, completely unpredictable fluctuations. Maybe your eye level just shifted slightly when you were reading a thermometer, or a tiny draft in the room affected a super sensitive scale. They happen, and this is exactly why we take repeated measurements and calculate averages. It smooths out those random little bumps in the road. A truly great investigator is always looking for continuous improvement. So, at the end of your evaluation, you should always be suggesting modifications. Say you were doing a thermal experiment. You might suggest adding better insulation next time to reduce thermal energy loss to the room. Doing this proves you understand exactly how the experiment could be tweaked to yield even more accurate results the next time around. Finally, Section 5, Ideas, Evidence, and Controversy. Let's look at how these tiny lab techniques actually drive massive historical paradigm shifts. It literally took centuries of meticulous, painstaking observation to shift human understanding of the universe. I mean, think about it. We went from the ancient Earth-centric model proposed by Ptolemy all the way to 1543 when Copernicus finally said, hey, I think the sun is actually at the center. Later, Galileo used new telescope technology to back that up and was actually imprisoned by the church in 1633 for saying it. It really wasn't until Isaac Newton introduced gravity and then Einstein refined mechanics in the 20th century that these models fully crystallized. The takeaway here? Scientific interpretation is a fierce, constantly evolving battle of ideas and hard evidence. Another huge point, sometimes the impact of a brilliant observation isn't felt immediately. The source material points out that it took years and years for the scientific community to recognize the profound health dangers of X-rays and radioactive materials. Why? Well, simply because cancer takes a really long time to develop. Science requires immense patience. Sometimes it takes decades for the full picture to finally emerge. And, even today, just providing concrete scientific evidence doesn't automatically mean society is going to accept it. Whether we're looking at the potential risks of microwaves from mobile phone networks or the complex, heavy data surrounding global warming, there can often be massive pushback. People can be reluctant to accept scientific findings, especially when there are deep-seated social or economic interests at stake. Science just doesn't exist in a vacuum. It happens right here in the messy real world. The text sums it up beautifully. Many scientific theories have had to wait for new data, technological inventions, or time and the right social and intellectual climate. So as you go out and conduct your own lab investigations, no matter how small they might seem, ask yourself this: what hidden truths might your own data reveal, if only it were given the right time, the right technology, and the rigorous methodology to finally shine?